All right, so section 2.3 is going to be it's a combination of things. If you've been following along in the class, it's not too difficult because it's basically going to summarize everything we've talked about and show how they're related to each other, all in this one massive theorem that you're going to have to memorize by the end of the class, okay? So we'll start off the invertible matrix theorem. I'm going to try out a new handwriting font because my other handwriting is really, really hard to see.
You can just change it. I didn't know you could do that.
Invertible matrix theorem. Okay. So there are going to be A, B, C, D, E, F, G, H, I, J, K, L parts to this theorem. Okay, but it sounds like a lot, but most of them you can immediately either tie definitionally to the concept, or it's something that's just summarizing a major point that we've already made in the class, okay?
For formatting reasons only, how long is each one of these points?
Oh, these aren't very long. Like, okay. I have to list it out like a stack and then the rest of the stack, but each one is only going to be about maybe that.
Oh, perfect. Yeah. Thank you.
Okay. So, let A be a square n by n matrix. Then the following statements are equivalent. So what I mean by that is, if one of them is true, then they all imply each other. Am I recording? Okay.
Do you use OBS for recording?
No, I'm using like the photo booth on, whatever the free stuff. Okay, so the first thing is we'll start, if I say that A is invertible. A is invertible. So if this statement is true, all of the rest of them that are going to be written down are also true. So what I think I'll do is I'll just write them down and then give everyone a chance to write them. And after writing them down, I'll talk through how we can kind of motivate and understand why all of them come from this statement. And then I have a flow chart that I made, I think it's my freshman year, that I've now resuscitated from the dead and put on the D2L shell. So it's the whole thing, so you can download it, you can save it for your notes. If you miss something, then it's all going to be there. So A is rho equivalent to the identity corresponding. This was the entirety of the lecture pretty much last time. We were talking about how A being invertible means we could get it to look like this, and then that actually was part of the procedure for getting my inverse, computing the inverse. A has n pivots, or n, I could say, pivot positions. And again, if you're rho equivalent to an identity just by definition, when you draw up the identity matrix, has a pivot for every single row, and since identity with n rows is going to have n pivot positions. So this isn't really something new, it's just a consequence of B, which is in itself a consequence of A. D here, when I make this equation AX is equal to 0, quick vocab check, this was called homogeneous equation. This then has only the trivial solution. Okay? Why might that be the case? Well, if we're rho equivalent again to an identity, and that means we have a pivot for every single thing, guaranteeing the existence of there being a pivot position means you're never going to run into the circumstance where you clear out an entire row with zeros. Because when we did clear out an entire row of zeros, that meant free variables, and free variables meant that you could have more than just the trivial solution. But if I'm basically definitionally clamping down that no, I'm never going to have a free variable. No free variables, okay? So then you're stuck with that. You're stuck with the trivial solution. See the part E here? So then when we defined linear independence, knowing that this equation has only the trivial solution was part of how we defined what it meant to be linearly independent. So I could say that the columns of A form a linearly independent set. Okay, so how do I get here? Well, again, the way we defined, and if you flip back in your notes and you found that section, yes.
Just to stress, you said the columns of A is in the matrix, because then after it says form A is linearly independent. Both
I'm
A's
realizing that this font is terrible now. Okay, no, yeah, so good question. The columns of the matrix A form a linearly independent set.
Okay, so second A is not a matrix.
Yeah, this is just the word
Making sure.
Yeah. I'll underline this one. This is the matrix.
Wouldn't like the brackets.
Okay. Also, this marker's good. Okay.
Are you feeling it now?
I'm kind of feeling this marker. I'm not gonna lie. Okay, so X, the transformation X to AX is 1 to 1. Okay, so if our invertible, we're 1 to 1. But how would I get from here? How do I know that? Well, remember when we were talking about there being an invertible matrix? If there's an inverse, essentially, we can think of this AX equals B idea as just, well, undo what you just did. So there's always a way to get back. And that correspondence just then, therefore, for each input, I can go backwards to its singular output. So that's always going to just correspond 1 to 1. Yeah.
Probably dumb question, but what does linearly independent mean?
Okay. Well, so the definition of, go back in your notes to when you wrote down the definition of what it means for a set of vectors to be linearly independent. Okay. And part of that definition was saying that the vector equation, essentially, if we wrote it as a homogeneous equation, only has the trivial solution. So what made a set of vectors linearly independent was that if I organize them into this homogeneous equation, the only solution I'm getting is the trivial solution. So that was the qualification that definitionally made that linearly independent. So when we talk about linearly independent, you could really think of E as rephrasing D with different terminology. Okay. There's G. Is it hard to see down here for the background?
Yeah.
Oh, because of this.
Is there any way to lower the height of the monitor?
Go steal the table.
I will keep this in mind, and then before the next lectures, I can move.
Yeah, I can go to the left.
Yeah, but I don't want to hold it's corded to the thing.
You want me to help you pick it up? And,
No, because it's like corded to the thing.
Yeah.
Yes. AX is equal to B. Has at least. Oh wait, I switched font on me.
Oh no.
I mean, it's not. No, I mean, change font.
Okay, G has at least. One solution. No matter what I choose, so for all B in R N. Okay? No matter what I choose for this, I'm guaranteed a solution. Well, why might that be the case if I'm invertible? Well, to say I'm invertible means I can basically always do this. There exists an inverse, so I'll just invert both sides. And that's always going to cancel to the identity. And identity times anything is just anything, so that's always going to exist. This has to exist, definitionally, from A having an inverse. Okay, so that's what we mean. It doesn't matter what B I choose, so long as it's the right size, I can just perform this algebraic manipulation because this has to exist by definition. Okay? So do you see the reasoning there? So always try to read under the hood whenever they say something like this. You can kind of get behind the rationale, and it'll help you memorize these. A, B, C, D, E, F, G, H. The columns of A span R, N. I think I was talking with Nathan after a class, and he was kind of thinking about if you had a set of linearly independent vectors, then certainly since you're able to access all of the possibilities, then doesn't that just definitionally mean you span the space you're going into? Yes. And since that's exactly what's going on, we have a linearly independent set of vectors as columns, well then yeah, so definitionally then, they're gonna span and reach every single possible vector here. A, B, C, D, E, F, G, H, I. The transformation x that takes into AX maps maps Rn onto Rn. Okay, it's a bijection. In other words, we have onto and one-to-one. I switched fonts. Did I switch anywhere else? Okay. There exists an n by n matrix C. Okay, now if you were present in lecture on Monday, then these next two that I'm about to write should ring the familiarity bell nice and loud, because this is precisely how we defined invertible in the first place, okay? There exists an n by n matrix C such that C times A returns me what? This is part of the definition.
AC.
Not quite. Okay, think about it. A is invertible. And by the nature of being invertible, there is guaranteed the existence of something that returns me to what?
Identity.
Yes, identity. Thank you. That's part of the definition. Okay, and this is, remember that matrix multiplication doesn't commute. So I can't just conveniently say that multiplying on the left will always be the same thing as multiplying it on the right. So I have to separate this out. There exists also an n by n matrix. We can call it D, doesn't matter. Okay, so that now I can multiply it on the right as well as the left. What does that return me? By definition, I, the identity. And then the last one here was the last property we covered in last lecture, is that the transpose then is also invertible. And you might be thinking, how do we make that jump? Well, think about the operation to get from A to A transpose has a way to undo it by simply transposing again. Ergo, there's a built-in inverse in the way that transpose is even defined. So if the original A is invertible, then yeah, sure, performing a reversible operation is reversible, doesn't change anything that would make this suddenly not invertible and have a way to go back. Okay? So this is the start. This does expand over the course of the whole semester to, I don't even remember how many parts. It fills an entire page, and I mean, it's recording, so there's not much I can say, but okay? All right. Are there any questions about this written out so far?
I just wanted to clarify my, so basically for J and K, we're saying that C and D are the inverse of A.
Yes.
Right, okay, cool. I just wanted to make sure.
Right. So the reason, the only reason why we have to split, and that's a good question, the only reason this entire horrible mess of having to split a left case versus a right case is because you are never allowed to do this. You are never allowed to say that AB is equal to BA in general. Okay, this just can't happen with matrices. And because this can't happen, ideally we'd be able to just say, okay, well, CA got you back to I. Fantastic. And we would be fine if these commuted. So don't get thrown off by the invention of new symbols. They're just placeholders for the fact that I cannot commute.
Right, okay.
But that's a good question, yeah. I like that question because it brings out something in the way theorems are built. They are precise, detailed enough, never redundant. There is not a single detail on here that is extra information, and it is the bare minimum amount of information that is logically preceding. That's math, okay? No fluff, no extras, just what logically follows and the logical necessities, what is necessary to be true in all cases, okay? Actually, what do we think about the font? I kind of like the font. Yeah, it's much easier to read than my other chicken scratch. Okay.
Does that mean our matrix A is not going to be lowercase, just for clarity?
I might.
Or are you going to italicize?
I might either underline. If it's not clear from context, I'll underline it.
Right.
Okay. So, yeah, funny story. That's like the entire section. So, but here's the thing, though. What I'm going to do is I'm going to show you the implications, so that you know how things go, and then.
We can do our homework.
No, I'm going to show you this flow chart.
Okay.
Yeah, I'm going to show you I'm going to annotate through the flow chart, and then that'll help. Okay, so everybody have this written down, please. Does everyone have this, like, a sheet of paper with every single statement down? Like, if you have it on your paper, give it away. Woo! Fantastic. Okay, so keep that as reference. Keep that as reference as we go to the flow chart, okay? And let's walk through the flow chart. So so we have this, right? If I erase this, you have a copy of it on your paper, yes?
Okay.
Because I am more than willing to wait 5 minutes for everyone to write this down on a piece of paper. So yes, we all have this. Thumbs up? Okay. Please.
I'm kidding. I was kidding. I was joking.
Okay. Okay. You know how people. I don't want to say this on the recording, but I'm gonna. There's a sense of the boomer judgment that's kind of like whenever any person who has an age that is less than theirs, you're basically an infant in their eyes. And so it's like we're college students, right? We're getting ready for a real adult life. And they're like, oh, you think you're busy? Wait till you have children. Wait till you have to parent. Wait till you have to. I teach math. I will be ready. Oh yeah. Didn't hear you the first time. Wouldn't be my first rodeo. Okay. Who likes flowchart? Okay. The Invertible matrix theorem flowchart. I like the flowchart, because it's going to take 2 whiteboards of information, and it's going to condense it into something that actually kind of makes more intuitive sense, I would hope, than just brute force memory. Have you ever seen question?
Is this going to be like a half page or a full page?
I'm going to probably use both sides of the board here. Yeah.
Okay, so like for us, right? Do I need to I have like a third of a page left. Do I flip it over? Or
Flip it over. Yeah, fresh page. Have you ever seen the videos of the really, really fancy domino chains where they spend like $100,000 on dominoes and they just make them do this crazy art? And there's all these different things that are going everywhere. And it all comes because they just knock over the first domino. That is this. The first domino is declaring that your matrix is invertible. And then you can follow, and it will split into different threads, and you follow those different threads. But ultimately, it all comes from one domino knock, okay? So, Okay, let's see. Is there anybody particularly artsy who knows how to? Jessica, can you please come here? Yeah, woo! How does this map onto the board in the least horrible way?
Okay, so if you do, so I'm just gonna draw dashes where you should write
Okay.
stuff. So do A is invertible, then down, and then the next box, then down. Then there's another box here. There's another box here. Then these are arrows, by the way, guys.
It's like witchcraft. I'll never.
And then that box is
More boxes and more lines. A thought bubble.
Dang, wow. That's Renaissance.
Okay.
3, 4, 5, 6, 7. Yeah.
Thank you. Okay, thank you so much. All right, everyone, give Jessica a hand. Thank you. Okay, so we're gonna fill in all of these pieces. Now I have a template to follow. Wow. You guys, when God gave you the ability to see stuff in your head without actually it being there,
That's like a superpower.
okay. Would you like to share with the class, Prem?
Yeah,
Okay.
Say it with your chest. Say it with your chest, son.
I heard it, but I'm not really well. Can you say it?
Okay, so this is the first box. The first domino. A is invertible, okay? So when we define this, through the perspective of matrix operations, then we understood that, okay, because of this, then there's this C, where CA is giving me the identity, and there also is some D, where AD gives me identity as well, okay? So that's the first direction you can think of this. You can interpret our invertibleness in this sense.
Is A invertible, is that the box that's in the top,
Yes,
top
that's
row in
this
the
one.
middle?
That's this one.
Perfect.
That's the head. Because all things are flowing from that.
Absolutely.
Okay, so this is our matrix operations. Then, by definition, we have that transpose thing. So I have that AT. It's kind of funny because the way the flowchart writes, it's kind of like it takes the last components that I wrote and then does them first, but whatever. This is also invertible. And this is because the transpose operation. Transpose of a matrix. Okay, so we have matrix operations for the existence of my left and my right multiplying. I have the transpose giving me that the transpose is also invertible. So now, our favorite, row operations. Row operations. What kind of insights do the row operations give me? Well, that tells me in our procedure that our matrix, if invertible, can be reduced to the identity matrix. And part of that implies, so these kind of go together, that A has how many pivots? Yeah. Okay, so I can get from invertible, knock down the next domino for row operations. A, it's got to go down to the identity. That's the whole purpose of that one algorithm. And by doing that, we've essentially assumed, logically, that therefore there have to be n pivots. There's no other way that works. Okay? So now, we don't have to only think about our row reduction system with augmented matrices. We can think of this as matrix equation. So I could think of this as the matrix equation. In the matrix equation, here we have AX is equal to 0 vector. What solution, what's the only solution we are going to have? Trivial. So this is trivial. And because of that, the other version, so this is homogeneous case, the non-homogeneous case, AX equals B, this has, this always has, I'll word it like that, always has, this will imply, I'll keep it parallel with it. So this equation implies that we have trivial solution. This equation implies that there exists x is equal to A inverse times B solution. So this works. Okay, and so this little speech bubble thing is to include this. Is that here's a memory help that connects these two together. The memory help is just simply, what is an identity matrix? Right, so for example, if I did this in R3, I have 1 0 0 0 1 0 0 0 1. So then I'm thinking to myself, well, I didn't have to draw this in 3 dimensions, but this is convenient for example. How many pivot positions are there always going to be in these identities? Well, the same number is the number of rows. So that's going to help me with this, and it's also going to help me, how does that help me with this? Well, because the matrix equation, when you look at the augmented here, I have now 1 0 0 0 1 0 0 0 1, and then those B values. So I'm thinking about this. I'm thinking about if I'm row equivalent to the identity, get this mental picture in my head, so that I'm thinking about something tactile, something concrete, not just like floating around concept, then the moment you lock that in, the concept of there being n pivots comes for free. It's one of those self-evident things proof by, open your eyes and look at it kind of thing. And then because of that, the moment I start introducing this to matrix equation situation, so if I want to augment the 0 vector or a B, say I put the 0 vector here, 0 0 0. Well, again, when you look at it, you're like, well, so x3 is 0, x2 is 0, every single one of these is just going to be 0. That leaves me with only one possible solution, the trivial one. Question. Is that something that you have to really memorize? I mean, you could, and you should, but this is going to make that a whole lot easier. It won't feel like random information, you're memorizing a behavior. And then if I stick in some B, you'll notice I'm going to have my solution. I'm not going to run into the contradiction of 0, 0, 0 equaling some non-zero constant. We've put the safeguard in of always having that pivot so that there will always be a way to get our unique solution. Okay, so this little speech bubble, does this little speech bubble help some of you guys relating row operation to matrix equation perspective? Okay. And then just 2 more boxes to go to is the linear independence line of thinking. So as soon as we knock over this domino and we talk about this, then we've intruded on the territory definitionally of linear independence. Okay? So down here, down the linear, linear is not spelled L-E. Okay. Linear independence. Alright, so down this perspective, then my columns of A, so I'm going to use the conventional notation to save space. My A1 through AN. This forms what type of set? Oh, okay. Linear independent. How do I know? Well, when you study and review your definitions for exam 1, for linear independence, the definition will basically state that if you have your homogeneous equation, only having trivial solution is how we define linear independence in the first place, okay? So at this stage of the invertible matrix theorem, we're not really doing anything with the theorem. We're just recapping definitions and then restating them because they happen to be logical consequences, okay? And then another consequence from that, which we should start calling this the Anderson consequence because he brought it up first, is that if you're linearly independent, then you're able to access all of the other b's. How do I know that? Because no matter what b I choose, I can find a way to get to it, okay? What does that mean definitionally? You've spanned your entire space. If you're able to access every single b, and you're able to choose an x that will always get you to every single b no matter what b you chose, then realistically, choose any possible b, take up all of the vectors in your Rn space. That is what it meant to span it. Okay, so we've spanned taking these columns A1 to AN is going to be just Rn. And then the last thing over here is the perspective of linear transformations. So we've done row operations. We've done the fact that we can perform operations, do algebraic computation with matrices. We've talked about the operation of transpose. From row operations, I can think just realistically about all the way back in chapter 1 what it meant to set up these augmented matrices to think about my matrix equation and get at my conclusions. From thence, I essentially accidentally produce the definition of what it means to be linearly independent, which forces us into the conclusion, think about this. Homogeneous gives us the definition. Non-homogeneous version essentially implies this. They go together, they're pairs, it's symmetric. And so now the last perspective here was the linear transformation perspective. So, linear transformation. Which is that we have those two special properties, one-to-one and onto. So x into ax is one-to-one. This is shorthand for one-to-one. And x is onto. So we have both one-to-one and onto. So we like being able to take inverses. Having the existence of inverses is nice because with the existence of inverses, you can perform familiar algebra. That's kind of the whole point. So that's why this is so crucial. Okay. So again, thank you, Jessica, for that. Because without that, this would have looked impoverished. Like I can't even begin to describe. Okay. Just out of curiosity for me as a teacher, which made more sense? Talking through the listed items of the theorem or the picture?
And the picture obviously listed.
Okay, raise your hand if you like just the listed theorem. Okay. Raise your hand if you like the flowchart perspective then. Yeah, very balanced class. Okay, cool. So I will continue to prepare both in my notes then.
Aww.
Okay. No, the way I like to do my SOS is in the lectures so that the feedback can actually impact your current education instead of not your education. That's good. Just a personal opinion. Okay. I recorded that. Oops.
You don't think that like some dean or something is going to go through all the hours of
I'm not going to say much, but I do have some form of relationship with the dean.
Okay.
Good or next.
Some might say I have a relationship with the deans.
Are we getting around to it?
One of the
No, I want to graduate actually. I do want to. Okay. A few things.
We have
Few
to
things.
repeat it in
This will be helpful when you're doing homework. So if A and B are both n by n, such that, again, I'm using this as such that their product spits out the identity, okay, then what are we allowed to conclude? Well, we are allowed to conclude that A is B's inverse, yeah?
Yes.
And what can I say about B?
A's
A's inverse. So keep that in mind, all right? Let's do this definition, even though it's kind of obvious, but it was in the book, so you might as well see it. A linear transformation T Rn to Rn. Notice now that I'm n and n instead of m and n because we're talking about invertible matrices, so it needs to be square. This is invertible if and only if there exists some transformation S, Rn to Rn, such that, this is another abbreviation that's really useful to use for inline, such that for all vectors x in Rn, this is going to look very familiar to what you did in like high school algebra 1, okay? S of t of x is equal to t of s of x is equal to x. Okay, sure, am I using a vector here instead of just a typical x? But when you had algebra 1 and it was f of g of x and g of f of x gave you back x, that was just how you did like your SAT math problem for, are these functions inverses of each other? No different with mappings, okay? So that reasoning is still the same. I would call S is the inverse with respect to linear transformations. Oh, I didn't underline invertible, sorry, invertible. Of T, and we can then denote it as just T inverse. So we don't have to use the S notation anymore. I could just say T inverse, so I could say T of T inverse is the same as T inverse T, which will always return you your X. Okay. Questions, comments, concerns?
Potentially stupid question, PSQ. So when you say transformation and then you say R of n goes on to R of n, that basically means that when you're transforming, you're keeping the same number of columns, right? Is that what that indicates, or is there what does that mean basically?
Good question. Remember that no matter what, these were just indicating how many entries were in those vectors, right?
Okay, right.
So this is saying vectors with n entries, two vectors with n entries.
Mm-hmm. And so
So-
you're transforming in the same format, basically.
Yes. So we're allowed to stay. We're allowed to map in the same space, the same size space.
And vectors with the same entries, when building that into a matrix, that means that those vectors become columns, right?
Yes, the
Okay.
vectors then are. We can think of that as the column vector perspective.
Right.
Yeah.
Okay.
And since it's always going to be n entries, then we would typically have n vectors inside by n, so
Right.
square. Yep.
Thank you for that.
Okay. Questions about really anything in the entire class up to this point? Because this is a really, really good section to catch up on stuff if you're behind. Because this is kind of going to pull together old stuff. Nothing here is actually new. Everything here is technically, one could even say this was your exam review. Okay?
Oh.
Word on the street. But, okay. Questions about the operations, the algebra, the rules.
So what is the on the bottom rightish box? There's a 1-1.
1-to-1. 1-to-1.
1-to-1.
That's a shorthand for 1-to-1. That'd be the same thing if I wrote out in English 1-2-1.
And what that's basically saying is that x x becomes what is that saying? Is that
Okay.
sorry,
Yeah. Recall in the lecture notes from the time we talked about linear transformations that this arrow, special arrow, is a shorthand for defining a transformation T, R and Rn in this case, of x being taken by T of x is equal to Ax.
okay.
So this is simply saying that T of x is equal to Ax in a linear transformation. Yep.
Because T's a transformation. And so when below that where you say is onto, is that saying that it's the transformation of x?
Yeah, the transformation T specifically has the property of being onto.
Okay.
Yes. And then the top line would be then saying that transformation T has the property of being 1-to-1 as well.
Thank you.
These are good. These are good. Any other questions? Okay. Well, in that case, what I'm going to do is I'm going to stop this.
I got one more question.
Okay, yeah.
So for that box, can you explain the
This one?
the flip. I don't know. I'm dyslexic. The bottom one, the other bottom one. So the linear independent one, right? So you're basically saying that because the thing that's times the x's in the equation can be modified by multiplying it, therefore it can be the span. Is that what you're kind of saying?
Where I'm getting this top line is I'm just citing the definition of what linearly independent is.
Okay, cool.
So that was the first thing that I want you to do is go back to the book, go back to your notes, go to this definition, and then as soon as you read it again, this is going to click because this is just a restatement of the definition.
Sorry, could you repeat what you're saying with that top star theorem?
Oh, yeah. So if I take two n matrices where their product is I, the whole annoying thing about how we couldn't commute so that we had to come up with two separate things is now it's saying even though we can't commute, the language we use to express two matrices that multiply to I, we are allowed to call them each other's inverses. So I'm not allowed to say that AB always equals BA. But I am allowed to say that if their product is the identity, then A it can be called B's inverse and B can be called A's inverse. Under the hood, this is implying that if you have invertible matrices, their inverses can commute. So essentially, this is also BA. But only because they're each other's inverses.
So if AB equals I, you can guarantee BA will also equal I?
That's basically the force of this little theorem. And the argument for that can be made through these. Because all I would have to do is substitute B inverse in here for A, and now I have B inverse B equals I. And if I chose to substitute A inverse in for B, now I have A times A inverse, which is definitionally I. Just leave it.